Hello everyone, this is the part 3 of the tutorial of the Fluent setting up a mixing fluid in a pipe. So in the first video I showed how to create this geometry. Then in the second video I went through the meshing, different sets of the meshing and create the mesh. So we have our mesh and we have updated the mesh to Fluent. The only change I have made is I changed the maximum size of the meshing from 3 to 6 millimeters to have the Fluent simulation faster. So when you update your mesh in the workbench, you will have a check mark in this mesh section. So now we have updated our mesh, we can set up our Fluent simulation. Double click on the setup, and I have 8 processors on my laptop, so you can set the use the parallel version. If you have just one CPU, you can use the serial version. Make sure that you check this double precision. I have an Intel machine with Intel CPUs, and I have installed the MPI of the Intel ANSYS MPI. So if you don't know what type of MPI you have, just leave this as default. But if you know how to install the MPI, it's better to install the Intel MPI and choose the Intel MPI because it's more compatible with your CPUs. It depends on what type of CPUs you have. So I will run the Fluent and start setting up our problem. So if you refer to this picture, we have a inlet flow with 0.4 meter per second speed, and the temperature is 20 Celsius. The turbulence intensity is 5%. We have another inlet with 1.2 meter per second, temperature is 40, turbulence intensity is again 5%. So this is the properties of the fluid, which is closer to liquid water. I will set up this problem in Fluent. So now our mesh is loaded to Fluent. So basically we should go through this 3 of the simulations for each section to set up our simulation. So in the first step, in the general, it's better to check our meshing. If you have any warnings or errors, if you don't have a good quality mesh, Fluent will give you an error or warning. So we are going to have a steady state simulation. We are not considering the gravity. In the models, we need to since we want to have different inlet temperature and get the temperature at the outlet, so we will turn on the energy equation. So for fluid, for viscous simulations, we will go to the, let's double click on this one. So I will use the K epsilon model, so which is the turbulent 2 equation, K epsilon model. In some again, the turbulence simulation is a very specific simulations. You need to have the physical understanding and set up the these parameters. I will use the enhanced wall treatment and keep the other settings as is. So this is basically the same settings it's mentioned in the Fluent tutorial. So I will click OK on this one. So I have set the models. So I will go to materials, double click on the materials. We have air as a fluid and aluminum as a solid. We don't have any solid domain here, only we are going to have a liquid domain. So I will go to Fluent database. You can create some user database too in the fluids, I will go down to liquid water and copy this to the current simulation. So now we copied the water liquid here. We will go to the cell zones. As you can see, we have one cell zone. The name is solid, but the type is fluid. If you check the type here, it's the fluid type. So click on edit. So as you can see, this is defined as air. So we will change this to the liquid water and click OK. So basically we defined all the this domain as water. So we will go to the boundary condition, double click on this. You can group them by zone type. So you have two inlets here, the main inlet and the smaller inlet. So the main inlet, let's see our problem. Okay, here the main inlet is 0.4 meter per second and 20 Celsius. So we'll the type of the boundary condition inlet automatically is defined as the velocity inlet, because we have the name inlet in the naming from the meshing. So if it's not, you can change the type from here, or just go here, right click on this and change it the boundary condition type, but it should be a velocity inlet. So it's 0.4 meter per second and temperatures 20 Celsius. So this is Kelvin. We can convert units, or it's easier to go to temperature and change the units in Fluent. So now this is Celsius, so it's 20 Celsius, and the turbulence intensity is 5%. So if you see, the turbulence intensity is 5%. And it's better to do with the intensity and hydraulic diameter. So let's change the length unit to millimeters. So our diameter is 100 millimeter. So let's define as the 100 millimeter. So because we know the hydraulic diameter, so it's kind of better defining the turbulence in the inlet. Click OK. Go to the small inlet, which is the velocity inlet again. So change this one to intensity and hydraulic diameter. Intensity is 5, hydraulic diameter is 25. We have 1.2 meter per second with 40 Celsius temperature. So 1.2, and we will define this as 40. Click OK. And for the outlet, we have the pressure outlet. So if we click outlet, we have the pressure outlet with the gauge pressure of the 0, which is atmospheric. So we defined our boundary condition. The other things you can change in your simulations are defining the solving methods. So in the solution section, we can click on the methods. So you can choose different schemes. I'm going to choose the simple. For the gradient, green, Gauss, node based. These are like mostly Fluent settings to understand which methods are you going to use. It's better to read CFT books, numerical CFT books, or Fluent help and kind of theory and manual. So I will leave others as is. So the other part, we can create some report definition in Fluent. So I will explain why I'm going to create a report definition, we can monitor a specific property. For example, here we are going to monitor the temperature at outlet, or we can go to surface max or average. Let's do face maximum. Okay, so I wanna create a temperature, face maximum temperature, static temperature at outlet. So I want to report a file, create a plot, print the console every one iteration. So let's do every two, so we will have less number of outputs. So in steady simulations also we have like convergence criteria, which is in the monitor sections, in the residuals you can define. You can also monitor one of your properties to see if this number is not changing. It means that your simulation is almost converged. So I will close this one, and I will go to initialization here. So I will do the initialize. So I will go to run the calculation, number of iterations, let's do 300. So then click calculate. So it will take a while. I will fast forward this calculation part and get back to you when it's done. Okay, now the simulation is done, and we can check the results. First, the residuals, you can see that according to that criteria, based on the monitors residuals, it's converged. And if you see that the maximum face temperature at outlet is kinda converged to a number after 100, almost 125 iterations, but then after that it stayed the same up to the end of the simulations. So we can create some plots inside the Fluent, but to have a nicer plot, it's better to go to CFT Post or the results to visualize the plots. Okay, now it's finished. I will double click on the results. This will open up the CFT Post. So you can see these rings. It's a kinda frame of the geometry. You can turn these on to see the geometry, but I would like to turn them off. So let's create a plane. So I will create a plane on XY axis. So I will create a XY plane. You can see this is the plane. So I can turn off this plane, then create a contour on that plane. So domain is all domains. The location, I will define the plane 1. Let's like create the pressure. You can see that we have a higher pressure here. As you go, it's going smaller. Or if you plot the velocity, local velocity. You can see that it's all, we had 1.2 here, so we have like 0.2 here in the velocity, and it's kind of mixing together. Let's plot the temperature, local, and increase number of the counters to 50. Okay, you can see that if we change this appearance from scientific to fixed, and just want to fix these numbers. As you can see, we have this plot of the temperature. So you can see we have a low temperature with 20 Celsius. If you remember the problem, we have at 20 Celsius here mixing with the 40 Celsius, so creating a mixture here. So we can do different stuff, like we can let's turn off this counter, create the streamlines, create OK, streamlines. So we can create other visualizations. For example, let's turn off this counter, and we can create streamlines like all domains, starting from inlet main. So let's click OK. These are the streamlines from inlet 1, and let's create another streamline starting from inlet 2 or the small inlet. Click OK. So to show both the streamlines together. So, and you can rotate this. You can go to animation, select both the streamlines, and click play. You'll see that let's click stop. You can go slower, and options, the size of the spacing, let's do 0.1, the size is 0.3, and click OK. You can play. So you can see kind of representative of the fluid particles or particle-like animation. So you can stop this one. Okay, since we have smaller spacing, so it will take time to stop. So turn off these streamlines. So you can change these balls to 3D arrows, and let's increase the spacing to 0.5. So since we turned off the streamlines, let's go to the streamlines, symbol show streams, turn off the show streams. We need to okay. So if you play, you will not see the lines. Okay, we need to increase the size of the arrows. Let's put 2 here. So you can see the arrows as the velocity vectors. It's kind of symbol of velocity vectors, you can see. And we can stop this and like color these with variable, like change of those with temperature, and click apply. Also stream 2, and change the variable temperature, apply. So if we play this, we have the coloring of these arrows with the temperature. So you can see that it's red and blue. It's kind of shows the temperature. So you can get many different cool animations, you can also stop this, turn the counter on, and play the animations while the counter is on. So you can also go to options and kind of change the size, and you can save a movie from your animations and those kind of post-processing. So thank you for watching this video. In the next video I will show you how to do the parametric study in Fluent, and in the future videos I will show you how to change the mesh size, dynamic mesh size, based on the different gradients. So for now, the next video will be the parametric study in the Fluent. Thank you for watching. Please subscribe to our channel, and you can watch the previous videos to see how to generate the geometry, mesh, and set up the Fluent simulation. Thank you.